Hello dear students. So today I will discuss the next topic, slip of a induction motor. To understand the slip of the induction motor, so let me revise the working principle of a three-phase induction motor. So what happens in the working principle? So when I give three-phase input supply to the induction motor, then the rotating magnetic field is produced in the stator. Okay, whenever this rotating magnetic field passes through air gap and cuts by the stationary rotor conductors, then an EMF is induced in the rotor. So that tends to flow of electrical current in the rotor. So because of the short circuited rotor, so this current again produces its own magnetic flux. So now there are two fluxes in the machine. One is the stator flux, that is called rotating magnetic field. Another one is the rotor flux, that is because of the induced EMF due to the stator magnetic flux. So whenever these two fluxes are additive, and that area will becomes the high flux area. Whenever these two fluxes are opposite in direction, then two fluxes will be cancelled with each other, so that area will be the low flux area. So this high flux area develops the torque in the induction motor, so that tends to rotate the rotor in the direction of the stator magnetic flux. Okay, so there are two speeds. One is the speed of this stator magnetic flux, also called as RMF. The speed of RMF is also called as NS, synchronous speed. And the speed of this rotor, the shaft is rotating, means that is the speed of the rotor, also called as the speed of the induction motor. So that speed we can measure with the help of N, that is actual speed of the induction motor, and another speed is synchronous speed of the induction motor. So practically this speed, the synchronous speed is always greater than the actual speed of the induction motor. So this N never catches the speed of Ns. Always it is nearest to Ns, but it's never equal to the Ns. So here comes the concept of slip of the induction motor. So we have seen rotor rapidly accelerates in the direction of RMF, rotating magnetic field. Okay, but in practically the rotor can never reach the speed of the stator flux. Stator flux means RMF. Rotor speed means it is the speed of the induction motor, actual speed. So if it did, then what happens? There would be no relative speed between the stator magnetic flux and the rotor conductors. Hence, no induced rotor currents, and therefore no torque to drive the rotor. So simply the motor will comes to stop. It will slow down because of the friction and windage. Hence, the rotor speed N is always less than the stator field speed, that is RMF speed Ns. So the difference in the speed depends upon the load on the motor. So how much load is connected to the motor? So based on that, the N and Ns differences depends. So now the difference between the synchronous speed Ns and the actual speed N, that is called slip of the induction motor. The difference between the Ns and N is called the slip. Usually the slip will be measured in percentage. The percentage of slip is equal to Ns minus N by Ns into 100. So this numerator Ns minus N is also called as slip speed. Or in other words, we can understand slip means why the word slip is used, because this, if an observer is sitting on the Ns, means on the stator flux, so he will see that N is slipping back with respect to the Ns. So that's why the slip speed is Ns, difference between the Ns and N. So I will continue the next topic, that is the effect of slip on the frequency of rotor current. So when the motor is stationary condition, the frequency of rotor current is equal to the supply frequency. It means that if the rotor is not running, means the induction motor is not running, in that condition the frequency of rotor is same as that of the supply frequency. Means if you are giving input supply frequency is 50 Hz, then under stationary condition the frequency of rotor is also 50 Hz only. But when the rotor starts revolving because of the induction, so when the rotor starts rotating, then the frequency depends upon the relative speed or slip speed, because we know the equation Ns is equal to 120 F by P. So the frequency is directly proportional to the ns, synchronous speed. So that's why let us consider at any slip speed the frequency of rotor will be f dash. Then what happens? The slip speed is ns minus n is equal to 120 f by p is the actual equation, but I have taken f dash. This is the rotor frequency. And the another equation already we know that the synchronous speed ns is equal to 120 into f by p. So take the ratio of these two equation. So what you will get? Dividing equation number 1 by 2, we get f dash by f is equal to ns minus n by ns, which is equal to this is nothing but what? S. ns minus n by ns is equal to slip s. So now I can write f dash is equal to f into s. So the frequency of rotor, f dash means the frequency of rotor is equal to slip times the frequency of stator. F means the frequency of stator, f dash means the frequency of rotor, s is the slip. So there is a effect of slip on the rotor frequency. That is the meaning, f dash is equal to sf. But in the transformer we have studied the frequency is never changes in the input and in the output side. So the frequencies remain same, only the voltage can be changed. But in induction motor the frequency of stator and rotor is same only when the motor is not running, that condition. If the motor starts running, then there is a effect of slip on the induction motor. That's why slip times the frequency is equal to the rotor frequency. Okay, this is very important. So this helps to solve the some numericals on the slip of the induction motor.